All right, it's 9:40, so let's get started. So how many of you actually did homework 1 or some of the problems? Okay, that's good. So part 1 closed last night, and part 2 is due a week from last night, I guess. Quiz 3 will be out tomorrow, so just giving you a heads up. And solutions to quiz 2 and what we did last week in recitations are also posted on the website. So any questions before we get started? No questions? All right. So what was the major thing we talked about last week? Yeah, these things called NFAs. Wait, what's an NFA?
Non-deterministic finance.
Yeah, it's these non-deterministic things, right? That's terrible. All of deterministic finite automaton. So what was, I know the deterministic finite automaton part, but what's the non have to do with it?
We don't know what next state's going to happen based on the input, right?
Well, in terms of we don't know means it will make a choice, right? There's some choices that will be made. So what are the types of choices that can be made?
Should be subset of all.
Well, it always will be a subset of the states, but how do I make a choice in an NFA? How is the choice made?
We don't make any choice, we keep all the states active.
We're not quite there yet, but for an NFA, we'll always make exactly one choice. But how does it make a choice? Well, what choices are we allowed to have? Well, do we always have to read the input? No, we could have these things called what? Epsilon transitions, good. Transitions, right? We're allowed to have these where we can have a transition where we don't read the input at all. But what other kind of choice can we have?
To read the input?
Yeah, something about reading the input, but what kind of choice may I have? For a given state, I may have many transitions on the exact same symbol, whereas a DFA only had exactly one. But here, I may have a situation where some state has 2 transitions or more on the exact same symbol. So, multiple transitions on same symbol. All right, I need a stack. All right, so we have this model, which is exactly the same as deterministic machines, but we have this added power here. So what was the thing that we were able to show with NFAs?
They can be converted to a DFA.
They can be converted to a DFA. So what was the basic idea and how we did that? So let's say we have an NFA right here, which I'm going to call N, which has states Q, sigma, delta, Q0F, and want a DFA, I'm going to call D, with states Q prime, same alphabet, different transition function, different start state, different final states. So how did we define the states of the DFA then?
Power set of Q.
Yeah, power set of Q. So why would we want to call it that? Why would we want that? It was one of the suggestions earlier that when we have these multiple possibilities, I may go to a bunch of states, or not go to a bunch of states. I have the potential to choose any number of states, right? I may have a bunch of choices. So I may not need every single state in the power set, but why try to limit this at all? So might as well just let all of the power set be here. So the idea here is that the states of the DFA are going to represent sets of states in the NFA. So let's say that like this was Q1, it went to Q2 and Q3 on the same symbol. Then we can say, well, any state that involves Q1 in the set, in the corresponding set, then if we look at the transition on input A, then whatever state it's going to go to is going to include Q2 and Q3 in that set. Okay? All right, so that's pretty easy. Alphabet's the same. Transition function I'll do last. So what about this new start state? Well, I'll ask this a few times. So what do the states in the DFA represent as for the NFA? The sets of states, yeah.
I think you have written wrong, like, NFA should be DFA over there.
But I want a DFA here. Yeah. So I'm looking at the start state of the DFA in terms of this.
So how can Q not?
Q0 prime is the start state of the DFA. Yeah. Any other questions so far? Okay. So, what are the states of the DFA representing NFA? Well, there's sets of states in the NFA. So I better write down a set here. Well, what would be a good representative set for the start state of the DFA then? Well, I hope it better include the start state of the NFA, right? Because I want to start in the same place as the NFA did. So I'm going to make this Q0. But is there a problem with this? Yeah, what's the problem with this?
It's all transition.
Oh yeah, I may have a situation where the start state was right here, and I have epsilon transitions coming out of it to some other states. And so without even reading anything, I may end up in one of those other states. It may make a choice to go to one of those other states. So I gotta close all those other states with via epsilon transitions, and that's called the epsilon closure, yeah. And we call that the function which is called E, and it takes a set of states of the NFA, and it produces a set of states which will be a state of the DFA, which represents for every state in here, I can go to other states via epsilon transitions. All right? So if this was Q1 and Q2, then in this particular case, the epsilon closure of just Q0 would be what?
0, Q1, Q2.
0, 1, and 2, yeah. Right, because I better include the state itself that I'm going from, because I don't have to take those epsilon transitions if I don't want to. Questions so far? All right, so let's do final states. So how do I determine if a state of the DFA is a final state?
So if any single state in that set of states is
Right, right. So let's say, for instance, in this example, that Q1 happened to be a final state. So how would I determine if this state of this is a state of the DFA now, if I were converting it? How would I determine if this was a final state? Well, the suggestion was, well, there is a member of the set that is a final state, which is Q1. So that means that there is some way to get to this final state, right? There is some way to get there, so therefore I should make that state of the DFA final, right? Because the point of non-determinism is, if there is a way to eventually land up accepting, it will make the correct choice, right? So if there is a way to get to Q1, as it says right here, there is a way, then I will make the correct choice, okay? So that's why I make that one final. So how do I represent that formally? Well, let's look at every single subset of the set of states of the NFA, and then if any one of those in this subset X happens to be final, I'm going to make that a final state, right? Remember, X is going to be a subset of Q, which is the set of states of the NFA, But what does it represent in the DFA? It's a set of states in the NFA. What does it represent in the DFA?
A set.
A single state, remember? Because each state in the DFA is a set of states in the NFA, right? So I better look at every single subset of states in the NFA. This represents a state in the DFA. Well, how do I determine if there is such a member of X such that it is a final state? Well, there's got to be something that's in common between this subset X and the set of final states of the NFA, right? There better be something in common. Well, how do I check if there's something in common between two sets?
The intersection.
Intersection, right? So I look at the intersection between X and the set of final states. Well, that's F. So if this intersection, well, if there is such a member, then what can I tell about the set? It better be non-empty, right? If it's non-empty, then there is something in common. Well, if there's nothing in common, then this intersection's empty, which is exactly what we want. Okay? Okay, so let's look at the transition function now. Let's see. So remember, transition function takes what? It takes two things. State and input symbol. What do the states of the DFA represent in the NFA? Set of states. So when I'm going to write S here, that is a state of the DFA, but it represents a set of states in the NFA. So, and the symbol, let's just say, is the symbol A. Well, how do I determine what's going to happen here? Well, remember, the output of the transition function is a state of the DFA, but that's a set of states in the NFA. So, if I was looking at, say, what delta of Q1 on A was going to do, actually, let's look at it this way. Let's look at the transition function with Q1 and Q2 on input A. So how do I determine what's going to happen next based off this set of states right here? What am I going to do with each one?
Follow their transition input and then you
Right. I'm going to look at each of the members of the set and say, okay, Q1, where do you go on it? And I'm going to put that aside. I'm going to look at, say, Q2, where do you go on A? And I'm going to add that to my current set of states. And I'm going to union all of those together. Okay? So, well, this is a set. So what we're doing is we're looking at each of the elements in here and unioning all of their transitions wherever they go. So let's do a giant union over every single element in S. Well, let's just look at every single little q in S. So remember, S is a set of states in the NFA. So Q then is a state of the NFA because it's every single element of this set. So how do I determine where this little q goes on input A? Oh, this should be prime, sorry. Where do I determine in the NFA where this little state Q goes on input A?
The original delta function?
The original delta function, yeah. So that tells me what it would have done on input A. So that's where I'm going to look. So every single element of this set S, I'm going to union all of them together, and then I'm going to have a giant set. Is that it? What was that? Oh yeah. So remember, I may have a situation where, let's just say I'm looking at Q1 on input A, but obviously it goes to Q2 and Q3, but these may have epsilon transitions. So I may be able to read a character, but I also could follow those epsilon transitions and not read anything else. So what do we have to do? We have to take the epsilon closure of the entire thing again. Okay. Any questions about any of this? Yeah.
If transition goes to the empty state.
What do you mean it goes to the empty state?
So, because in the NFA, you have
any set union the empty set is still the original set. So there's no problem there. Any other questions? Cool. So what are the other things we were able to show with NFAs? There were two other things we were able to show. Closure under concatenation. So if I have two languages and both of them are regular, I can give an NFA for the concatenation of the two languages. So pick any string on the first one, any string on the second one, put it in the concatenation. Their concatenation in that order in there. What else were we able to show? Closure under star, yeah. And so we'll see how to do that. Is there another one that we could also show? We didn't show it, but we could also show? What about union? So this is actually something that we didn't cover, but it's actually pretty cool. If I have two DFAs right here with their start states, how can I recognize their union? Well, I can do the product construction, but do you know of an easier way with NFAs? Yeah, I'm going to make a new start state, and epsilon transitions to the old start states of the two machines, like this, right? And that actually gives us the union of those two languages. So we didn't even need to do the whole product construction. We could just have this really small addition to the two machines, which is pretty cool. All right, any questions about any of this? All right, so let's actually do some of the problems on the handout. So the first one is, I want all the strings in 0, 1 star such that W is the concatenation of X and Y, and X contains the string 0, 0, and Y starts with the string 1, 0, 1. Okay? So what do you think would be a good strategy when you look at this?
Build X and Y out individually, I think.
Okay. So let's think about it. So all the strings in here are going to be strings of the form X concatenated with Y. Well, X, can we build a, say, a DFA for the first one that involves X, contains 0, 0? Yeah, sure. What about Y? It starts with 1, 0, 1. Yeah, we can do that. So can I do one for the concatenation of both? Yeah, so we'll see how to do that in a second. So how do I do the first one? Contains 0, 0. Well, do I need to build a DFA for this? It says show that it's regular. Do I need to build a DFA for this? No, why do I not have to make a DFA for this? Oh, we actually showed that DFAs and NFAs recognize the exact same set of languages. All right? So I can perfectly give a DFA or NFA for this, right? So let's build an NFA to make our lives easier. So can I make an NFA for the language X contains 0, 0? Yeah, and so how would I do that? Well, let's think about it. Suppose we have whatever string, and it contains 0, 0, followed by whatever after it. Can anything appear before the 0, 0? Yeah. What about after? Yeah. So let's just have a machine where it could read whatever at the beginning, and then non-deterministically guess, I'm going to transition on this 0, and then another transition on 0, to a final state where it can read all the other characters. So that's what we're going to do. Q0. So this Q0 is going to loop on all inputs, but it's also going to non-deterministically guess, oh yeah, this is the start of this 0, 0 sequence. So let's read a 0 here, then read another 0. And then we're going to go to Q2 where after we've read 0, 0, I don't care what happens afterward anyway. So Q2 is going to loop on all inputs again. Okay? So let's convince ourselves that this is right. So whatever string we have, is there a way to accept if it has 0, 0 in the string somewhere? Well, whatever happens before, it can make the choice of staying in Q0. And whenever it starts seeing the 0, 0, it will non-deterministically guess to start going down here, at which point we will accept anything. All right? Pretty straightforward, right? All right. What about the y starts with 1, 0, 1? Can I make an NFA for that? Yeah, how would I do that? Well, what does the first transition have to be? A 1, it can't be a 0. And the next one has to be a 0. Third one has to be a 1. But what about after that? I don't care, right? But once I get there, I will accept anyway. So let's make a Q3. Is the start state. It has to start with a 1. Q4 has to read a 0. Q5 has to read a 1. And Q6, I don't care what happens afterwards, so I better make that final with a 0, 1. But with some loops. Okay? Is everyone good so far? Okay. Well, how would I recognize the concatenation of these two languages then? Something about epsilon transitions. So, how would I well, I better read a string in here and better be accepted in here, then the second part of the string will be accepted by the second machine. Well, how am I going to transition over to the second machine? But should I read any input when I'm transitioning over? No, because then I may not be actually recognizing the actual languages, the original languages. So I better have an epsilon transition over. So from what state over here to what state over here am I going to do that? Well, it should be from Q2, right? Because I better accept in this machine first, then I better try to accept in the second machine. So I can only leave from Q2. And it's going to go to Q3 on an epsilon transition. Am I done here? Oh no, what have I forgotten?
You're moving them to CSE355.
Oh yeah, I should make this a not final state. Why should I not make this a final state? Because I have to accept in the second part of the machine. If I just accept prematurely, actually, this machine will not ever transition to the second part. And why is that? Whatever string it has, once it gets to 0, 0, it can just stay in Q2 forever, right? It doesn't have to transition over. So I better make this a not final state. Because I want to have it accepted in the first machine, then the second part of the machine will, accept the second part of the string. Okay? Everyone good with that? Yeah.
So for a language, we have accented 0, 0, right?
Mm-hmm.
That does not. So does that mean 0, 0 has to be in the middle of the string?
Wherever it appears in the string somewhere.
Can it be in the beginning?
Yeah, it can be the very first transition. It's just that the machine, since this is an NFA, obviously, it can choose to go to this transition if it sees a 0, or do this transition. It will choose the right one if there is a way to accept. So if there is a way to accept, it will either do this one or do this one.
So let's say you read 0, 0 and dot, 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 right?
Yeah.
So you would in Q0 first?
I may be still in Q0, but it may go over here. It depends on what happens afterward. But it will always make the correct choice if there is such a choice. Okay? I know it's kind of weird, but yeah.
Can you take out that 0, 1 transition on Q2 then?
No, because I don't want to modify this machine. Because it'll look for a way to accept if there is one. Well, if it stays right here, it'll never be accepting anyway. So if it ever wants to accept, it better go over here. That's why we made this not final. If we left it final, then it can just stay there forever and always accept any string, no matter what happens over there. Okay? Any questions about any of this? Okay. So let's actually construct an NFA for L star. So let's just look at a general method for actually doing this. So let's say I have a DFA right here, an arbitrary black box, and let's just say it has 2 final states. So how would I make an NFA for L star then? Remember what star means. It means pick a string out of the language as many times as you like, and then concatenate them, all of them together. So how would I recognize the star here? It's almost that. So the problem with that is that if I do an epsilon transition from the final states to this start state, I may be in the middle of a computation and may accept something. Oh, make a new start state. Yeah. So that's actually a great suggestion. And the other problem is that this machine, the start state might not even be final. What string do we always know is in the star of any language? Empty string. Well, we better accept that anyway. So let's make a new start state that is final. So therefore, we must accept the empty string. So what am I going to do with this new start state?
Well, do we need a different start state? I don't understand.
The reason we make a new start state is that we may not actually accept. The main reason is that I don't want to modify this machine at all if I can. Right? I don't want to add transitions between states within the machine. But the real reason is that I may, if you look through the details, you can actually accept more strings than you would have before anyway. I invite you to look at the details, but I want to modify the machine as little as I can. In some cases, you can't actually do that though. All right, so what am I going to do with this new start state? Right, I better try to modify this machine as little as I can, so I better have the ability to start in the original start state without having read anything at all, so I better need an epsilon transition now. Oh yeah, I also need a way of going back through the machine as many times as I like. Well, that means that I should be able to come from these start states back to the original start state. Via what kind of transitions?
Epsilon.
Epsilon transitions. Good. So from all the old final states, I'm going to add an epsilon transition to this new final, to this new start state. Okay? So how am I going to modify this example? I'm going to do it in place up here. So how would I modify this NFA that we made to recognize the star of that language? First step, new start state that is final. So I'm going to add a new final state, which is the start state up here. So I'm going to call it QF, make it final, make it the start state. So what am I going to do with this new start state?
Epsilon transition to.
Epsilon transition to the old start state. But what else am I going to do?
Epsilon transition from Q6 to QF.
Good, good. Epsilon transition from Q6 to the original start state. Am I done? Yeah, that's essentially the construction that we just did. And that was the only final state of the original NFA, so we're already done there. You good with that? Any questions? Yeah.
Did we get rid of Q6 as the final state, or keep it as the final state?
In this particular case, you can, because there's only one way to there's only one way to get to the final state. In general, you can't, And also, I don't want to modify the machine as little as I can. The whole process is trying to be algorithmic and not trying to be clever about this. But in this case, you can. Any other questions? All right, so let's do the final two examples, which are conversion from NFA to DFA. So this first one, so I don't see any epsilon transitions, so that's a good win. So we don't have to worry about epsilon closure for now. But, so what was the main idea of producing a DFA from an NFA? What was the really good strategy for being able to do this? Well, let's see, there are 3 states right here. And how many states am I going to make if I just did it naively? Power set. 8, yeah. 2 to the 3. So I want to avoid that if I can. I may need to, but I want to avoid that if I can. So how would I try to avoid that? Well, what we could do is, let's just start from the start state and then just build the DFA as needed. And then we would not create states that we wouldn't otherwise need. So let's try to figure out what the start state of this DFA, if I were to convert it, would be. So how would I figure that out?
It's just the start state.
Sorry?
It's just the start state.
Yeah, well, let's think. It's gonna be something related to Q0, the set containing Q0, but since there are no epsilon transitions, what is epsilon closure of Q0 in this machine?
Q0.
Just itself, because there's no epsilon transitions coming out. So I'm only going to have Q0 here as a state. All right. So now what am I going to do? I'm going to figure out where can I go on A, where can I go on input B, right? So there's only one state in here, which makes our lives easier, but we're going to have more states eventually. So where can I go from Q0 on input A?
Q2.
Q2, that's the only way. And we'll have to be careful because there may be multiple transitions on the same symbol. But there's only one here. So let's transition over to here. But we got to be careful again because the only state we are going to go visit is Q2, but then we have to take the epsilon closure of Q2 in general. But here we won't have to worry about that. So it's just going to go to the set containing Q2. What about B? Well, it goes over to Q1, and I don't see another transition. And I don't have a state called Q1 yet, so I'm going to make a state called Q1. I'll worry about final states at the end. So let's look at Q2. Where can I go on input A from Q2? Well, I can go to Q1, and I think that's the only one. Oh, I have that state already. So I'm just going to go to here. What about input B? Well, I could either stay in Q2, or I can go to Q1. I have a choice now. Okay, so what state am I going to go to now? I think Q1, Q2, right? The set containing Q1, Q2, because I can go to either one of those. So I'm going to make that state because I don't have it yet. So I'm going to make a state called Q1, Q2. Okay. Let's come back to Q1. So where can I go from Q1 on input A? Just back to Q0. So I already have that state, so we're going from there. What about input B? I don't think there is one. Oh, what state is that then? Oh, empty set, right? I may not be able to go anywhere, which in case we're going to go to the empty set. So I'm going to call a state empty set. What does the empty set do on anything?
Self-loop.
It just self-loops on anything. If I'm nowhere and I read something, where do I go? Nowhere, right? So I'm just going to self-loop on everything. That's nice that we were able to close off that branch. So let's go over here. Q1 and Q2. So where do I go on input A, let's say? So how am I going to compute this? Well, I'm going to look at Q1 and say, where do you go on input A? So where does Q1 go on input A? Q0. So I'm going to start writing down a set Q0. And I don't think I can go anywhere else on A from Q1. Now, where do I go from Q2 on input A? Q1. So I'm going to go to Q0, Q1. And I don't have that state yet, so I'm going to make it easier. On input A. Okay? Let's do Q1, Q2 on input B. Well, where does Q1 go on input B? Empty set, so we have nothing so far. Where does Q2 go on input B? Q1, Q2. So Q1, Q2 union the empty set. I think that's just Q1, Q2, right? When you add nothing, you still get the original thing. Oh, and I have that state already, right? So I'm just going to self-loop on this. Because the set just on input B goes back to itself because those are the only states I can get to anyway. Q0, Q1. Let's figure out where we can go on input A. So where can I go on input A from here? Q0 goes where on input A? Q2. So I'm going to start writing down a set. Q2. And I don't think anywhere else. Q1 on input A? Q0. I'm going to reorder this to make it easier for me. Q0, Q2, and I don't have that state yet, so I'm going to add it. Q0, Q1 on input B, where does that go? Let's see, Q0, 1B, where do I go? Q1. Q1 on B, where do I go? Empty set. So Q1 union empty set is, oh, it's just Q1. And I have that state already, so I'm going to transition over to here. So we only have this state. So Q0, Q2 on input A, let's say. Where does Q0 go on A?
Q2.
It goes to Q2, so I'm going to start writing that down. Q2 on A, where do I go?
Q1.
Q1, it looks like. So Q1, Q2. Oh, and I have that state right here. So I'm going to transition back up to here. Q0, Q2 on input B. Where does Q0 go on input B? It looks like Q1 to me. Q2 on input B? Q1 and Q2. Oh, I already wrote down Q1. So I'm just going to write down Q1, well, it's already there, Q2. Oh, and I have that state already. So this transition is going to be appended with a B because it goes back to the same set of states. Oh, and there's no other branch, I call it. So are we done? Oh, final state. So how do I determine whether something is a final state here? If it has Q1 in it. So it doesn't contain Q1, so it's not final. This one contains Q1 to me. So that's final. It doesn't contain Q1. Oh, this contains Q1. This contains Q1. Doesn't contain Q1, doesn't contain Q1. I think we're good here. Any questions on that? Cool. So let's at least start the next one. I'm not sure if we can finish. So just letting you know, this has around 13 states. So if you just make room for it. All right, so now we actually do have an epsilon transition, so we really do have to worry about that epsilon closure stuff. All right, so let's figure out what the start state is. So how do I find out what's the start state of the corresponding DFA? What's definitely going to contain, well, the start state here is Q0, so it's definitely going to contain Q0, but is it going to contain anything else? No, and how do you know that?
No epsilon.
There's no epsilon transition from Q0. So this is going to be my actual new start state. Nice. All right, so let's figure out where Q0 goes on input B. So where do I go on input B?
Q0, Q1.
Q0, Q1, so I'm going to start writing this down. But now, what do I have to do? Check for epsilon closure. So what's the epsilon closure of Q0, Q1?
Q0, Q1.
It's just itself, right? Because Q1 has nothing coming out of it on epsilon. Q0 has nothing coming out of it on epsilon either. So I'm just going to make a state like this on input B. Okay? So now is where it gets interesting. Q0 on input A. Where's that take me? Q2, right? So I'm going to write down Q2. So what's the epsilon closure of Q2? Q2, Q3. Both of those states are in epsilon closure. So it contains Q3. Can I get anywhere else on epsilon transitions? No, I don't see any other epsilon transitions anyway. So that's going to be my new state on input A. Okay? Let's do the Q0, Q1 branch. So let's figure out where this goes on input B. So where does Q0 go on input B again? Q0 on B?
Q1.
Q0 and Q1, right? Because I have the self with it. So Q0, Q1. Where does Q1 go on input B? Nowhere, right? Is that just at the empty set? Oh, that's just this set we had here. Epsilon closure of Q0, Q1?
Q0, Q1.
Itself, yeah. So, but I already have that state, so I'm gonna self-loop on that. Okay, Q0, Q1 on input A. So where does Q0 go on input A? Be careful. Q2, right? Does that include Q3?
Yes.
Does the transition function include Q3 in this case? No. It's the epsilon closure at the end that will include Q3. So I'm going to first write down Q2. Where does Q1 take me on input A? Q0. So I better include Q0. What's the epsilon closure of Q2, Q0?
Q0, Q2.
0, 2, and 3. Good. I'm going to reorganize this. So 0, 2, Q3. And I don't have that state yet. So I'm going to make a new state. Okay? Q2, Q3. Where do I go on input A? So where does Q2 go on input A? Be careful. Q1, Q2. Good. So I'm going to write down Q1, Q2. Where does Q3 take me on input A? Which one? Q4. Yeah, so I'm going to write that down. What's the epsilon closure of Q1, 2, and 4? It is itself plus what state? Q3, good. So I'm going to write down 3 and Q4 on input, I think it was A. Let's do Q2, Q3 on input B. Where does Q2 take me on input B? Be careful. Q2 on input B. Q1, Q4, so I'm gonna write those down. Where does Q3 take me on input B? Q3 on B.
To the south.
To the south, yeah, so I'm gonna write down 3 and 4. What's the epsilon closure of 1, 3, and 4? It's self, right? Because there's no, the only epsilon transition is from 2, but I don't have that. And I don't have that state anyway, so I'm gonna make this a new state. Like that. Okay? All right, let's do 0, 2, 3. So where does 0, 2, 3 take me on input A? Where does 0 take me on input A? Q2, so I'm gonna write that down. 2 on A, where does that take me?
Q1.
1 and 2, I already have 2, so I'm gonna write down 1. Where does 3 take me on A?
4.
4. What's the epsilon closure of 1, 2, and 4? 1, 2, 3. Simple as that. Do I have that state? Oh, I have that state already. So I'm just going to transition right over to there and hopefully not make this too much. Sometimes the diagrams are hard to draw with crossings and whatnot. But let's do 0, 2, 3 on input B. So where does 0 take me on B? 0 and 1. 0. Sometimes I remove the Q's and just write the numbers. 0, 1, that's fine. 2 on B, where does that take me?
1 and 4.
1 and 4, so I already have 1, so I'm going to write down that. 3 on B
Itself.
itself, so I'm going to write down Q3. Epsilon closure 0, 1, 3, 4.
0, 1, 2, 3.
Yes, actually, yeah, you're right. So 0, 1, 3, 4, I don't have that. So Q0, Q1, Q3, Q4. Unput B. Oh boy, this is starting to get big. All right, 1, 3, and 4. Where do I go on input A? 1 takes me to 0, so Q0. Where does 3 take me on input A? To Q4. Q4 on A, where does that take me?
Empty set.
Empty set, so we're done there. What's epsilon closure of 0, 4?
0 itself.
Itself. So I'm going to have Q0, Q4 here on input B. Lot of branches here, right? 1, 3, 4 in input B. Where does 1 take me on B? Doesn't look like anywhere. 3 on B, where do I go?
Itself.
Itself. And so I'm going to write down Q3. 4 on B,
Nowhere.
it looks like nowhere. So I better make a state Q3. B. What? Q3 on it, let's just do Q3 by itself. Q3 on B, where do I go? Itself. Oh, that's good. Q. Not going anywhere else in that. Q3 on A, where do I go? Q4. And that's on closure of Q4 itself. So I'm going to go to Q4. Q4, what do you think it does on anything? Empty set, yeah. So we can see a few shortcuts like this. And we know that the empty set just loops on everything. Oh, at least one branch is out of the way. That's good. 0, 4 on input A. Where does 0 take me on A? To Q2. Q4 on A, where does it take me? Takes me nowhere. Where is the epsilon closure of Q2?
Q3.
Q2, Q3. Do I have a state Q2, Q3? Oh, I have that right here. So that's really, really nice. So that was on A. Q0, Q4 on input B. Where does 0 take me on B? Itself, Q1, 0, 1. 4 on B, nowhere. Epsilon closure of 0, 1. So, oh, I have that state already. So I'm going to come back here. Nice. Let's do 1, 2, 3, 4. So let's do A. So Q1 on A, that takes me to 0. Q2 on A, that takes me to 1 and 2. Q3 on A takes me to 4. Epsilon closure of 0, 1, 2, 4. 0, 1, 2, 3, 4. Whoa. Oh boy, a lot of states. 1, 2, 3, 4, and input B. Where does 1 take me on B? Nowhere. 2 on B? To 1. 3 on B? To itself. 4 on B? Nowhere. Epsilon closure of 1, 3?
1, 3.
1 and 3. Do I have that state? Hopefully I do. No, I don't. It's finite, right? So I don't have enough time to finish this up, but this is almost the entire thing. I know it closes up right after this. So I invite you to finish this up, but what would I need to, let's just say that this was the final thing. What would I need to check about this? What's the thing I've left out? Final state. So how do I find what's the final state? Anything that's 0 or 4. So this is final, this is final, this is final, this is 4, this is final, not final, this is 4, this is 0 and 4, not final, both, this has it, this doesn't. Any questions about any of that? All right, I'll see you next week.